Hi, we're going to do some videos on Unit 1 and Unit 2 papers. This is the first one, Unit 1, that I'm going to do, and it's based on the June, well, it's actually, it says June on the website, but it's not June, it's the May 2009 Unit 1 paper. Okay. So here's the first question, and it says, which set of quantities is all scalar? Well, in part A, acceleration is not a scalar, so I can ditch A. Part B, energy, mass, and power. That looks promising. I hope it looks alright to you also. Extension, force, no, that's a vector. Weight, no, that's a vector. So we're talking about B because power is just energy divided by time, and both energy and time are both scalars. So the answer for that would be part B. Question 1 of this paper should be part B. Question 2. Material is described as not easy to scratch or indent. That is a hard material. Not easy to scratch is hard. Okay, tough has to do with how much energy it can absorb before breaking. Also has to do with how much it can deform, therefore. Stiff has to do with how hard it is to get any extension of it, from it for a given force. So it's very hard to extend. And plastic is related to toughness in the sense that you can deform it. You can deform a plastic quite a lot. But in the sense of plastic, it doesn't necessarily mean that it can take a lot of energy. It just means that it can be deformed quite a lot. Tough definitely means it can take a lot of energy, and so therefore hard here means it is not easy to scratch or indent. So question 2 would also be part B. Question 3. Always try to understand each question as well as you can, especially when you're doing practice papers, because this is useful revision. Don't just answer why the answer is what you think, but also look at all the others and define them so that they act as revision. Recapping also. Okay, a force of 24 newtons and a force of 15 newtons act at right angles to each other. So the size of the resultant is, so I need to get the calculator for that. 24 and 15 newtons are right angles. So I can go here and make a diagram of that. 24 and 15. And they're asking us for this guy, which is the resultant. And we know from Pythagoras so that the one we're interested in is the square root of those two, and I don't know what that is. Take out my calculator. So that comes out to 801, I believe. And so the square root should be 28.3. But everything is to two significant figures, so I guess it's just going to say 23 newtons in the paper. Let's have a look at what it says. Oh, no, they give it to us with 3 significant figures, and none of them is the one I just worked out, so I must have made a mistake. Let me go back to the working. Yeah, it had something wrong in the calculator, but the 801 was correct, and the answer of that square root is actually 28.3 newtons. So that was okay. So in other words, question 3 would be C, part C. Question 4, let's have a look. The graph shows how extension varies with applied force for a string. It's a nice straight line. I'm checking on the y-axis. This is extension. It's not absolute length, so it's how much it is stretching. So it makes sense that at zero force it's stretching no amount. That's okay. Sometimes you get this that it kicks off from here somewhere in the y-axis, and that is normally because here it says absolute length or just total length, not extension. It's good to see a straight line. It means that it's obeying Hooke's law. We haven't gone past the elastic point of the proportionality limit. Question 4 then says the stiffness of the spring in Newton meters is either one of those 4, and the stiffness you should know from this equation. You need an equation that relates force and extension, and that's this one, right? And so here they have the y-axis, they have the extension, and the x-axis is the force. So actually the y-axis should be on the left, and we should say x is equal to F over k. So if the y-axis, if you look here on the graph, the y-axis is the extension and the x-axis is the force, it means that the gradient is then, if we write y is equal to mx plus c, with c equal to 0, because the y-axis here, the y-intercept is 0, then the equation for a straight line is just y is equal to mx. And here don't confuse this x with the other x, right? In this case the y-axis is the extension, which we're calling here x, and the x-axis is the force, so this axis is this variable, and therefore the gradient is 1 divided by k, because f over k is the same thing as 1 over k times f, right? So 1 over k is the gradient. So we go to the graph and we calculate the gradient, which you do by the change in height divided by the change in length. Change in height is 6, but that's in centimeters. So 6 centimeters over 9 newtons, right? So to calculate the gradient, which is 1 over k, is equal to the gradient, which is equal to the change in y divided by the change in x. And that is 6 centimeters, which is 0.06 meters, divided by the change in x, which is 9 newtons. Don't need to convert there because it's in newtons. And this gives me 6.67 times 10 to the minus 3. So that's 1 over k, but they're asking me for k, the stiffness constant, so therefore k is the reciprocal of that. Which is that answer to the power of -1. When doing that to the power of -1, I get 149.99 etc. Newtons per meter is the unit of k, right? Because if A is equal to kx, then k is equal to F over x, which is newtons per meter. So that's basically 150 newtons per meter, and I'm hoping that's going to be one of the options. There it is, 150. Good. So that's part D. Sorry, that's the answer to part 4 is part D. So then we'll just put it here somewhere. Part D for question 4. Let's get on with question 5. Says the energy stored in the spring when it is extended by 6 centimeters is one of those. So let's see, by 6 centimeters. I'm not even going to look at the answers yet. I think it's better to not look at them first. Do your calculations and then check with them and see which one agrees. But if you look at them too early, sometimes they can be misleading. So I tend to think it's better to try to solve it first and then have a look at the answers later. So energy stored when it's stretched by 6 centimeters. So the stretching is 0.06 meters. That is going to be a delta x, right? Or here we've been using x, so let's continue to use x, but it's a change in length that we're looking at really. Let's say then that the extension x is 0.06 meters, and the formula for the stored energy, which you should know, is 1/2 k times the extension squared. Sometimes you see the delta x squared. So x we know, k we just calculated, so assuming that we understand we're on the same question still, so we should do here 0.5 times, so 0.5 times 150, I'm going to take the whole number if possible, times x squared, which is 0.06 squared, so this is 1/2 times 149.99 whatever, all the number, times 0.06 squared, and that should give me the amount of potential energy stored. I'm just going to pause that for a second while I calculate it so I don't bore you. And it comes out to be 0.2699, so 0.27 and energy is in joules. So we have an option that says that, and it is 0.27 joules, so it's part A. The answer to question 5 is then A. Good. Question 6. The graph shows how kinetic energy varies with distance for a train accelerating from a station. So as distance increases, the kinetic energy increases. Both of them linearly. Now, distance is increasing, we don't know how. The distance could be increasing in any way. It could be increasing as we are accelerating, or it could be increasing as we're going at a constant velocity. And it's not going to be increasing obviously if we're stationary, but we don't know how we're moving, but we just know the distance is somehow it's increasing, and as it does increase, the kinetic energy is increasing also. So the question says, the quantity represented by the gradient of the graph, which is the change in energy by distance, is given by one of these four. And I just realized I've done one of the classical mistakes, which is good to show them off in such an unstylish manner, but anyway, I didn't read the question properly. Look at what it says. The graph shows how kinetic energy varies with distance for a train accelerating from a station. So we already have a clue. We know that the guy is accelerating, which anyway makes sense, because otherwise if it was going at a constant velocity, then the kinetic energy wouldn't be increasing. Kinetic energy is only increasing if your velocity is increasing, so there must be an acceleration. So anyway, that makes sense. And now, so let's think about what the gradient of this thing is. Okay, I'm going to talk a bit about this one in a bit of detail, because it's worth examining properly. So they have something like this, where this is kinetic energy and this is distance, and they're asking us what the meaning of the gradient is, and they're allowed to do that without having necessarily seen this graph before, but they're allowed to do that because we can work it out from using common sense, but we need to take it step by step. We can't just guess. So okay, so the best way to explain this is if you imagine a graph of, for example, velocity and time, then the gradient of a velocity time graph, as you should know, is the acceleration. What happens if you multiply the gradient by the time, by the change in time? So the gradient times the time will give you, so a times t will give you the change in velocity, right? Because the change in velocity divided by the time taken is equal to the acceleration. So if you multiply the gradient times the x-axis, you get the change in the y-axis, right? Hopefully that makes sense. So if I have dy by dx and I multiply it by dx, I get the change in y. So here there's a similar thing happening. Well, let's do another example. For example, current. If you have current and charge, you have current and time. Sorry, this is increasing charge and this is time. Then the rate of change of charge with time is current. T, that's the gradient. If I multiply the gradient by time, that will give me the total amount of charge between one point and the other. Total amount of charge that has been gathered in whatever is increasing in charge. Here it could be a capacitor, it could be anything. So if you get the gradient of anything and you multiply it by the x-axis, you end up with whatever's on the y-axis. So that's what we need to make sure that we do here, is that whatever we say that the gradient is, we need to make sure that when we multiply the distance by that thing that we just said, we get energy. We have to get an energy out. Okay, that is the first thing that we need to make sure, that distance times something that gives us energy. The other thing is, this thing is increasing in kinetic energy, and that's because an engine is doing work, right? If I have an engine and it's doing a certain work, it needs to be doing a force over a certain distance, and that's going to be the work done by the engine. And if we're ignoring air resistance and all the other friction effects and all of that, then all of the work done by the engine is going to go into an increase delta kinetic energy, right? And that increase in kinetic energy is what we're seeing here. We're seeing an increase in kinetic energy over distance. And so if I want to multiply the distance times something that gives me energy, it's going to have to be the force. Okay, distance times force, it needs to give me, then it gives me energy, and that makes sense. It will give me the increase in energy, and it makes sense that the work done that I put into the system comes into the kinetic energy of the thing that's moving, right? That's the only place where the kinetic energy of the accelerating train, I think it was, yeah, that's the only place where it can come from work being done. Now let's think about the logic of this also, just so we squeeze a bit more of juice out of this question. What about if the kinetic energy was like that? What does that mean? If the gradient is bigger, it means that the kinetic energy is increasing a lot more in the same distance. So in order to do that, I need to give it more velocity in shorter distance, because kinetic energy is half mv squared. The only way that I'm going to give it more velocity in a shorter distance is by having a bigger force, and so the gradient is bigger. Conversely, if we had it like this, then the change in kinetic energy over distance is very small, so I'm increasing the velocity very slowly as far as distance is concerned, and therefore I need a low force. So it makes sense that the gradient is proportional to the force, or is equal to the force in this case. And this question really assumes that there is no friction necessarily, because otherwise it wouldn't be such a nice straight line, unless the force is constantly increasing. But that's not the case, because this is a straight line, so a gradient has a constant force. Straight line has a constant gradient, so it has a constant force here. Anyways, hopefully all of that gives you a bit of insight into the idea of gradients and x-axis and y-axis. So the gradient of anything times the x-axis always needs to give you the change in y. Okay, you can think of other examples of graphs of things if you want, and hopefully that will make sense. Another one is the force is equal to kx one. This is force, that's x. If you plot it that way around, F is equal to kx, so the gradient is then k, right? So it makes sense that k times x times the gradient is equal to F, which is the formula, right? That's a normal k. This would be a big K, a very stiff graph, and this would be a not very stiff spring or whatever it is that you're measuring this for. Okay, hopefully that makes sense. The other idea that sometimes they ask for is the areas of graphs, and the area of graph is different. The area of graph is always the multiple between these two. Multiple between that and that would be the area. So in the case of velocity and time, then the area of a velocity time graph is always distance, and that's because velocity is equal to distance divided by time, so distance is equal to velocity times time. Velocity times time means the two axes together multiplied give you some other quantity. That means that quantity is represented by the area of the graph. Okay, so in this case you would have to do a triangle divided by a square divided by 2, or a rectangle divided by 2, or whatever. Same thing with the energy stored in a spring. You have the x and the F, and the energy stored in the spring, sorry, the multiple of X is the work done, so that would be the area there. The area there would give you, and that's why you can do it like this, half Fx, which if you express it as a k, since F is kx, then that comes out as half kx squared, and that's because F is equal to kx. Right, but the area of that graph is the work done to stretch it, and also the energy stored inside of it, assuming that it's all stored. That's a bit of revision on area and the graphs and gradients meanings. Hopefully that will be handy. Okay, so summary of all of that waffling is that the answer to that question should be force, and we should find that there's an option here for the force, because the force times the distance gives you the gradient, times the x-axis gives you the y-axis. Where is the paper? Okay, here, so force is B, so that's good. So we can go here now and type the answer for part 6 is B. Great. Running out of paper, let's see if we have enough for question 7. Says a car of known mass has a constant acceleration. Okay, so constant acceleration. The resultant force acting on the car can be found by applying, well, hopefully you know that one. Which of the laws has to do with the acceleration? Well, if there is a constant acceleration in the car, then this equation is satisfied. So if we know that this is a constant and we know the mass, then the resultant, Fr, can be found just by ma. And so this is Newton's second law. Hopefully you can recognize it as that, and it says that the rate of acceleration of the rate of change of momentum, really, but it's normally expressed like this: the acceleration of an object is proportional to the resultant mass acting, resultant force acting on it. So that would be Newton's second law, and so the answer of question 7 would also be B. Let's go on to question 8. We'll do just the 10 first questions in this video and then go to the next, because otherwise it will be too long. Okay, so what's question 8? Use the following graph. That's a very important sentence. Use the following graph to answer both questions 8 and 9. So that's going to be in mind. It says the graph shows how the velocity varies with time for an object. So velocity is going up at a steady rate, meaning constant acceleration, and then it is a constant velocity for the remaining of the time. And it says the total distance traveled by the object in 4 seconds is how much? Well, let's see. The distance of a velocity time graph I just mentioned is the area, the distance covered. So the area for the first 4 seconds is what they're asking us for. That is the full 4 seconds, so we need the area of the first section plus the area of the second section, right? The first section, let's check the units first. This is in meters per second, so it doesn't need conversion, and this is in seconds, so it's all fine. We're going to get the answer in meters. What do we have here? A change in y of 20 and a change in x of 2. And so that's going to be 20 times 2 divided by 2, because it's a triangle, plus 20 times the distance, the time between here and here. Don't take the full time, so that's another 2 seconds from here to here, and it's got 20 of height, so that's 2 times 20 again, but this time we don't divide it by 2 because it's a full rectangle, and so we get 40 divided by 2 is 20 plus 40, so that should be 60 meters in the first 4 seconds for question 8. So that is option C. So that would be option C. Question 9, which is based on the same graph, says the acceleration at 3 seconds is how much? So we need to find the acceleration at 3 seconds. Well, 3 seconds is here. What's the acceleration here? The velocity is not changing at all, so the acceleration is got to be 0. So there needs to be an answer here, an option that gives us 0, and it's D. So question 9 has answer D, which is nice and easy. Question 10. And this is the last question for this video. Question 10 says, okay, 2 springs. So I need to remember already what's going on with the springs. You should know, I mentioned this in a class, that I don't know what it's going to ask, but it's important just as a reminder that if this spring has stiffness constant K, then when you put them together like this, 2 springs identical, each one with K, then the combined, you had a weight here, the combined stiffness of those 2 together is 2K. Okay? But if you put them like this, if you connect them like this, then the way you add them is not so simple. And in fact, now that you've done resistances with me, the equation should look familiar. It is like this: 1 over the K of the total is equal to 1 over K1 plus 1 over K2. And that's assuming that they have different spring constants. Right here it would be K total equals K1 plus K2. And if there was more springs, you would just add them like that. But when you have them like this in series, you've got to add it like that, because actually the total stiffness is going to get less when this happens. The same as resistance, it get less when you put them in parallel. The opposite thing happens with springs. When you put them in series, the stiffness gets less. You can kind of intuitively see that this is going to stretch more easily than this guy, and than this guy, hopefully, which is the tricky one. Now, what happens when they're equal? K1 and K2, well, then you get 1 over K total equals 1 over K plus 1 over K, which is just 2 over K. And so if you flip both sides of the equation by multiple, you do a few multiplications, but you can see it as flipping both sides, then that's like saying that K total is equal to K divided by 2. In other words, by adding them in like this, you actually half the K. So you go from K to K over 2. And if you did it with 3, it would be K over 3. Same thing happens with resistors when they're equivalent. You have 2 of them in parallel, it halves. You have 3 of them in parallel, it goes to a third. So having said all of that, let's see what the question actually is asking. But this is important to know in case they could have asked us something like this. So they say, a spring extends by 10 centimeters when a force of 8 newtons is applied. The limit of proportionality is not exceeded. We can already use this information to find out the stiffness constant of that spring. 2 of these springs, meaning that they have the same properties of that spring. So before we look at the rest of the question, I'm going to calculate K for that spring. 10 centimeters and 8 newtons. That's the clue that they're giving us. So they're saying that the extension is 10 centimeters for a force of 8.0 newtons. So they're giving us 2 significant figures here everywhere. So F is equal to Kx, F is equal to Kx, and X is in meters always, so that's 0.1 of a meter, times K is equal to 8. So K is equal to 8 divided by 0.1, which is the same thing as 8 times 10, which is therefore 80. 80 Newton meters per meter, sorry. Yeah. 2 of the springs side by side and a force of 4 newtons is applied. What is the extension? Okay, so 4 newtons is applied. So let's have a look at what's happening now to K. Two of them are put next to one another, so K1 plus K2, since K are the same, it's just 2 times this K. So actually now the combined stiffness constant is going to be 160 newtons per meter. And so my equation is then F is equal to Kx, with F equal to what they give me here, which is 4 newtons. And they're asking us for the extension, so I'm going to rearrange it like this. F divided by K, which is 4 newtons they just gave us, divided by 160 newton per meter. So if I do that in the calculator, I get 0.025 meters. That's enough. That's 2 significant figures, and well, it's all that I get anyway, so there's no quarrel there. 0.025 meters, which is the same thing as, well, if it was 0.02, that would be 2 centimeters, right? And so this is 0.025, so that's 2.5 centimeters. Okay, it's not 25 centimeters. Hopefully you can see that. So that's 2.5 centimeters, and let's see what they give us here in centimeters. So 2.5, which is part A. So the answer for that is part A, and I'm going to stop now because the video is turning really long, and I'll have a look at the other questions in the next video or two, or 3, you never know. We'll continue with the paper. Alright, hopefully that was useful. Bye bye.